Transformers revolutionized the field of natural language processing, making applications like ChatGPT possible. Understanding their functionality starts with two initial steps: input embedding and positional encoding. Let's start with the basics. We begin with a sequence of text and start the tokenization process. This involves breaking down the text into smaller pieces, called tokens. Tokens are essential because they form the model's vocabulary, the elements that the model is trained to recognize and generate. By converting text into tokens, we enable the model to process and understand the language more effectively. This improved understanding leads to better performance in various tasks, such as translation, summarization, and text generation. During the mapping process, we are assigning for each token an identification value. The value is coming from the embedding matrix, a matrix with two dimensions. The first is the vocabulary, that identifies the total number of unique words we have in the dataset we use for the training. And second, the embedding dimension, that represents the length of the vector, however each embedding is considered a language feature. Going back to our example, for instance, each row corresponds to a word, and each column contains values that represent the word's meaning in a high-dimensional space. This is what we call the embedding vector. The values are learned during training. They usually start with random values and are adjusted through backpropagation, enabling the model to learn effective and meaningful representation of the input data, which improves overall performance on NLP tasks. Behind the scene, similar words will be placed in similar vector space. Let's summarize what we learned. We begin by taking the input text and breaking it down into individual tokens. Each token is then assigned a unique identifier. We retrieve the corresponding value from the embedding matrix for each token, and every token is matched with a dense vector that captures its semantic meaning, creating a rich representation of the word. By doing so, we obtain the input embedding matrix, a comprehensive representation of the entire text semantic content. Having the output of the input embedding, it will allow us to move into the next concept: positional encoding. Position of word within a sentence is crucial in large language models. The position helps the model understand context, maintain syntax, capture dependencies between words, and preserve the overall meaning of the text. Tokenization and positional encoding together enable the model to capture the nuances and complexities of language more accurately. Starting from our original sequence, now for each token we are going to extract the positioning and calculate, respectively, sine and cosine, using the formula on top of the matrix. The result will provide the positional encoding, and having the both matrices allow us to perform a simple addition to create the final output of this layer. The results will be used for calculating the self-attention mechanism. So, to summarize, we start with tokenizing the text, map each token to an ID using the embedding matrix, and then add positional encoding to this embedding. This final vector is what the model uses to understand and process the input.